Last time we were talking about the biharmonic problem, and we saw some challenges associated with that. We looked at this finite element, or this triangle called the Argyros triangle. It's actually the Argyros finite element, as a way of constructing a fifth order piecewise polynomial space, which was a C2 space or a C1 space, and therefore was what we call conforming. That means we could derive a finite element space based on these Argyros triangles, these Argyros elements, that was C1 and therefore was a finite dimensional subspace of the Hilbert space H2, which is what we need for the biharmonic problem. We discussed how to get the finite element approximation. That's the usual thing. We discussed the basics of Say's lemma and the interpolatory polynomial, et cetera, et cetera. Now we just have to put everything together, and we had to go through that part where we put everything together last time, but very quickly, and we didn't get all the details. Here I'm going to spend about 5 to 10 minutes reviewing those details, those um, estimates that we didn't quite get to talk about in any detail. All right, so just for a moment, we're sticking with the biharmonic problem. I hope you know what that looks like from the last lecture. We created an interpolant, and the interpolant was a projection into the space of piecewise polynomials of degree 5, such that the function such that the interpolant was also a C1 function. So in other words, we can create this finite element space VH, piecewise polynomials of degree 5, and this projection was a way of mapping smooth enough functions into that finite element space. The functions themselves had to be C2 in order for this projection to be well defined, because it required both first and second derivatives to work. In any case, we get an interpolation error estimate kind of the forms that we've seen before. This is not something we can prove or will prove, but something I'm simply going to state, and I can refer you to the literature or the appropriate textbooks for this. U minus that special interpolant that we talked about last time. This is again a projection or a way of putting a C2 function into the finite element space, the finite element space of piecewise polynomials of degree 5, such that the whole thing is globally a C1 function. So that's what this is, a global C1 function. I'm going to measure the difference. That's called the error in the norm HM. As long as the thing I'm measuring is rather smooth, it has to be an H6, then the interpolation error measured in the HM norm is less than a constant times H to the 6 minus M power and times the H6 semi-norm, as long as U is in H6. And M, what should we expect from M? M should be less than or equal to 5 to make this make sense. So if M is equal to 5, this would be H5, and therefore we get a first order convergence. If this is one lower, let's say H4, then I get a convergence order of 2, because 6 minus 4 is equal to 2. Now, in the problem at hand, we're going to need this estimate for M equals 2. That's because that's what Say's lemma tells us is the right size of the norm, the right order of the norm for our problem. It's order M equals 2. So for our problem, we just plug in M equals 2 and we get the interpolation result that we need. So again, remember that this interpolant requires the function to be C2. But if it's in H6, then there's no problem. H6 embeds into C2 in 2 and 3D. Say's lemma then guarantees that we have this type of error. Okay, so the error between U and its Galerkin approximation. Remember, this Galerkin approximation has to be globally C1. And for our purposes in our problem, it's a global C1 function that is a piecewise polynomial of degree 5 on each triangle. Measured in the H02 norm, we talked about that last time, is equal to the min taken over all V in the finite element space of the difference between U and V measured in the H02 norm. Now, that says that the finite element approximation is still the best approximation that you can possibly get when measuring this way. Now, H6 embeds into C4, so we're very safe in assuming that our function is C2. So this is a result of a Sobolev embedding. So let's write that there just so we have it. Sobolev embedding. That's what guarantees that we have this containment. So if it's in H6, then it has to be in C4. Therefore, this guy is well defined. We don't have to worry about that for as long as U is in H6. So let's assume that. Let's just take U to be in H6. And let's put these two facts together. So the error between our true solution and our Galerkin approximation using Say's lemma is less than or equal to that. Of course, if we pick a particular V from the finite element space, namely, we choose V to be the projection or the interpolation or the interpolant of U, now we have to measure the interpolation error. But now we have to do it in the H2 zero norm. But the H2 zero norm is a norm which is less weighty than the full H2 norm. So this is going to be bigger than the H2 zero norm if I replace that norm by H2 zero. So therefore, I can replace this with my interpolation error estimate and conclude this fact, that the error in my finite element approximation of the biharmonic problem, as long as H is in C6 and I'm using a fifth order polynomial for my approximation, is going to be of order 4. Okay, it's going to converge like order 4. Now, we can also use a Nietzsche-like trick to get a regularity boost. Or sorry, if we have elliptic regularity, we can use a Nietzsche's trick to get an order boost for our convergence rate because we can gain 2 more powers of H by going to L2, and therefore we get an H to the 6 convergence, or in other words, a 6th order convergence if we use piecewise polynomials of degree 5. So this is in keeping with what we learned for the simple approximation in 2D for our standard Poisson problem. We use piecewise linears, and in L2 we got H squared convergence, order 2 convergence, as long as we had an H2 function. So in other words, this order, full order, is matching this order. And the order of the polynomials is 5. We're essentially getting the order of the polynomial plus 1 for the overall order of convergence in L2. So in that sense, this seems to be more or less optimal. We won't talk anymore, at least for this problem, about optimality, but that is essentially optimal. So that's it for the biharmonic problem. In fact, from now on, we're going to deviate from the simple problems. We've looked at the standard Poisson problem, and the biharmonic problem. Both of those can be kind of classified as what we call elliptic problems. And now, from here forward, we're going to look at more exotic problems. Um, so the first one we're going to do are problems of parabolic type. So what's a parabolic problem? What's a standard example of a parabolic problem? The most common one that you'll see is the so-called diffusion problem. There, we're looking for a function which is globally, to make things easy, globally C2 over the domain omega bar. So that's the closure of omega cross 0t. So this is supposed to be space and this is supposed to be time. So this is sometimes what's called the prism or the what's another word for it? I've forgotten the other term for it, but in any case, this is space and this is the time that we're interested in. We're looking for such a function that classically pointwise solves this problem. Partial derivative t of u with respect to t minus the Laplacian of u is equal to some given function f in omega uh, for all time between 0 not inclusive and capital T inclusive, where u is equal to 0 on the boundary of the spatial domain omega for all t greater than 0 not inclusive less than or equal to capital T inclusive, such that we have the following initial conditions. So this is a boundary condition. This is an initial condition. So sometimes we call the diffusion problem an initial boundary value problem. Initial boundary value problem. This is the initial condition. We're supposing that in omega at time 0, u is equal to this known function. So this is a function of both space and time, I should say. That's a function of both space and time. Because I don't want to put the x in there to represent all the particular points of x, and I only want to represent particular points in time, I'm going to put a dot there where x normally goes. So f is a given function of space and time. V is simply a known function of space. Now, to properly pose this in the weak sense, I need to give you a little bit of more machinery from functional analysis. Or the theory of linear spaces, I guess. So we discussed this sort of stuff when we have a course, when we teach the course 547, which is applied linear analysis. So that's where this stuff would appear. You might also see this sort of information in a good course on PDE. If you have a copy of Evan's book from 2010, the second or third edition, second edition, I think, then all this is information is in there as well. All right, so the dual space of H01. Remember, H01 is a special type of Hilbert space. And what does the dual space mean? The dual space is the set of all bounded linear functionals on a space. So the dual space of H01 is a particular type of dual space, and we give it a name, we give it a symbol. So that's the symbol that we denote H minus 1. And we write H minus 1 is equal to the dual space of H01. So it's this object over here which we're defining. This notation here simply means the dual space of whatever Hilbert or Banach space we put inside the parentheses. And in this case, we're putting the particular Hilbert space H01. And I've already said this in words, but here it is in a sentence. The dual space is the space of all bounded linear functionals acting on a Hilbert space or Banach space. It could be a Hilbert space or a Banach space, doesn't matter. One can easily show that the dual space is also a Hilbert or Banach space if the space that you're originally considering the dual of is as well. So if H is a, so what I would say is if H is Banach, that implies that the dual space is a Banach space. And no, that's not correct. It's simpler than that, actually. If H is a linear space, then H prime is a Banach space. It doesn't even have to be a Banach space itself. Okay, so it's much simpler than that. Okay, so let's put that result in our pocket. Now, usually the dual space is equipped with something we call the operator norm. So what is the operator norm? And this here, just to make it clear, that's a prime. And usually the dual space prime, we try to angle it so that it's really clear that it's not a 1. Maybe I'll do that here as well. So I'm really trying to put a nice angle on that. So here's the definition, the usual definition of an operator norm. This one's for H prime, the dual space of H. We take the supremum over all phi in H not equal to 0 of the quotient absolute value f of phi divided by the norm of phi. If I take the supremum of that, that's going to define the operator norm of f. So for the present case, what is our operator norm? So our operator norm for H minus 1, that is the dual space of H0, 1, is the same, except we're replacing this by, this is the same. The only thing that changes is this guy down here. What is the norm on H01? It's just the semi-norm on H1. And so I've just replaced that with what it is. So this is the working definition of what we mean by the norm on this weird space we're calling H minus 1. So there's a minus 1 here. So this somehow should be evocative of the spaces that we have right now. So we have L2, H1, H2, and so on. And now where do we put this space H minus 1? Well, it's not really like the others. These are function spaces in the standard sense. These are standard function spaces. This one is a space of functionals. But it turns out that really, in terms of ordering, we want to put that guy over here. Why? Well, think about it like this. It's a little bit, it isn't easy to see this, so that's okay if you don't see it. This space H2 has one more weak derivative than the space H1, which has one more weak derivative than the space of L2. And in some sense, I can think of this as having one more weak derivative than the space of H minus 1. In other words, if I differentiate functions from this space, if I could, then they would be in H minus 1. Now, it's not exactly like that, but it's kind of like that. So in terms of a hierarchy, that's where H minus 1 goes. And because of that, it's a little bit like saying, well, usually, or not usually, but sometimes we'll write L2 as H0. So you can see that these kind of nest in numerical order. And then there are also other spaces down the order that I could consider as well. So that's kind of why this space is given the notation H minus 1. It's not exactly right though. So you don't have to write that down because it's not in any way rigorous. All right, so let H be a Hilbert space and let F be an arbitrary function, or functional, I should say, from the dual space. Then the following notation is what we call the dual pairing. And instead of using parentheses, we're going to use these angle brackets. Angle bracket is not exactly like an inner product because the order of what you put in this position and this position matters. So what I need to put in the first position is going to be a linear functional, and the second position takes a function from the, or takes an object from the Hilbert space, whatever it happens to be. It combines them and somehow produces a real number. So this object is called the dual pairing, and it's defined as, this is notation so far, but it has no meaning yet. It's called the dual pairing, and it's defined as follows. And this is going to be a weird definition for those of you who've never seen it before or thought about it. F against phi in the bracket in the dual pairing is just equal to F acting on phi. It kind of makes sense that it can do that. F is a function from the dual space. Phi is a function from the Hilbert space, so this is a real number. Remember, functionals are linear and bounded, and they take h into r. That's what a functional does. But it also, if it's in h prime, then it means it's a continuous function, or it's a bounded function, and it's a linear function. So we call it a bounded linear functional. Now we're ready to write out the weak formulation of this problem, the diffusion problem. By the way, why is it called the diffusion problem? It's related to the heat equation. You can see it's the same as the heat equation. It's also related to what's called Fickian diffusion, or a model that is that describes the diffusion of some sort of species, let's say, or a droplet of dye in a large pool of water. So this would be a good model of that. In that sense, because we're modeling the motion of droplets of a dye, or the concentration of some dye, then we don't call it the heat equation, even though it has exactly the same form. We call it the diffusion equation. But heat itself can be thought of as the diffusion of the temperature in some sense. And so in that sense, the heat equation is itself a type of diffusion equation. And so I call the whole thing, the whole mess, the diffusion problem, rather than calling it the heat problem or something involving temperature. Okay, so now we're ready to define a weak formulation of this. Now, if you've taken a course in advanced PDE, you've seen this, but I think most of you have not yet. And that would be usually covered in like 635. Maybe some of you are in that course now. And you may have seen some of this stuff in there, but otherwise it takes a little bit of time to get to the level of understanding some of this material from the PDE perspective. But as applied mathematicians, it's not hard to kind of figure out what some of these symbols mean, and we're going to put them together without doing all the proofs. All right, but first things first, we're here to make a definition. So I'm going to consider, I'm going to define the weak solution of the diffusion problem that I just gave above. And it's defined through the usual process. You take a test function, integrate by parts, and move things around. Actually, if I do that here, let's multiply by a test function, which is in space only, say v. It's going to hit this term like this. And if I integrate, then you can see I'm going to do what I usually do to the Poisson term, or for the derivative term in the Poisson equation. I'm going to integrate by parts and throw one of the derivatives onto the v. And so you'll see why we get what we're going to write. So let f be in this function space L2 0t L2. I have to explain what functions or what functions in this function space look like and mean, and I'm going to do that just below. For now, you can just think of it, it's a nice function. So given f in this function space, this is the time component, this is the spatial component, or reflects the time and spatial components or attributes of that. We're going to assume v is a simple L2 function. You already know what those things are. Then u is called a weak solution to the diffusion problem if and only if we need three things. And is it three? It should be four, and I'm missing one of the things, and you'll see what it is in a moment. Okay, so if and only if, number one, it has to be in this function class L2 0t h01, and I'm going to define what these spaces mean in just a minute. So for now, you can just think nice function spaces. U is a weakly differentiable function in time. Fine, you know what a weak derivative is. So we're just looking at the weak partial in time. But its weak derivative in time lives in a different space than the function u itself. We're going to say that this function has to live in this space, L2 0t h minus 1. So you notice that this one has spatial regularity in h01, but this one has spatial regularity in h minus 1, meaning this may be a function of time, but its values in space are those, or can be thought of as those, like functionals rather than functions in the usual sense. So that's a bit of an oddity for the moment. And finally, for almost every t in this interval, 0 to t, and for every test function phi in h01, it holds that partial t u, okay, the time derivative, against v. And you can think, at first, think about this as an inner product, but it's not really, right? It's dual pairing. And that's because du dt is, it has its spatial component is in h1, h minus 1, and that means it's a functional. So it can only be combined with objects from the Hilbert space through the duality pairing. And so that's why we use a dual pairing for that. Plus, this is the diffusion term after that we gain by doing integration by parts, gradient u, gradient v equals the L2 inner product of phi with f. And by the way, from now on, I'm going to get lazy because you can see what I'm doing is I'm simply dropping the L2 on the inner product whenever it's understood. So that's the only inner product for which I will do that. And so it's always understood that if I don't write anything here, it's simply the L2 inner product, kind of period. All right, now what are these functions? What are these spaces here? So I wrote a few of these in here, right? Here in my definition, and here. So what do they mean? What do these spaces mean? What do they indicate? So here's what they indicate. Let X be a Banach space. So this X I can think of as the spatial part of my function. So let X be a Banach space with the usual Banach space norm, whatever it is, denoted by the subscript X. The function space LP0tx consists, or this is, we're now defining this notation. It consists of all measurable functions. Technically, in the technical terminology, it has to be strongly measurable functions. Phi, taking points in 0t and mapping each one of those to a point in the Banach space X. So now I'm going to slightly shift my thinking. Remember, I have functions that appear like this. They're functions of space and time. Usually you write time second. I'm not sure why, but that's how it's usually done. I'm going to think about them in a different way. I'm going to think of every time I pull out a instance of time in the interval 0 to t, that creates a function in some spatial Hilbert space. And that's exactly what happens here. Okay, and if you look up above, every time I pulled something out of t, I would get a C2 function in space only. Here, more generally, I'm going to think about mapping from 0 to t into some space of spatial functions. So this is really depends on my spatial domain omega. So each time is kind of a temporal snapshot of a function in space. Each temporal snapshot is a function in space. Okay, and here's my space, my physical space over here. So this could be like H1, H01, H2, and even in the case that I wrote above, since this can be more general, this could be H minus 1, okay? Such that, and oh, by the way, I'm defining this for LP, and I should say here, it only makes sense if I'm doing P from 1 to infinity for this definition. I can also define this for P equals infinity. That's a slightly different definition. Oh, I forgot to say, what the heck did we miss with this definition? What did we miss with this definition? I forgot to put in the initial condition. I captured the boundary condition because the boundary condition is wrapped up in the definition of the solution space itself. But the initial condition is missing, so I've got to create some, I'm going to go in and do some surgery, and I will do that after class, and I'll put in the initial condition. I missed that. So this initial condition is missing from my weak formulation. It has to be there, but I missed it. So that would be 0.4. Somehow I only got 3 out of the 4 points. Okay. So strongly measurable functions, kind of changing our focus of them, thinking about a time-space function as being a function that takes an instant in time and maps it to a spatial function in this space X, which can be H1, H minus 1, H01, H2, continuous functions, and all the other stuff as well. Okay. I forgot to finish my point. Such that it's going to be a strongly measurable function such that its norm is finite. And what norm do we give these functions in this space? Well, it's a norm that actually makes sense. So for each time, I have a function that is in the space X. So therefore, I'm going to apply the X space norm to that. That's going to give me a number. I'm going to raise that to the p power. I'm going to integrate that from 0 to t, just like I would if I have the normal LP space. And then I'm going to take the 1 over p power. That gives me the norm on that space. That's the norm that has to be less than infinity. If you find that that's less than infinity for these measurable functions of this type, then we say that that function is in that function space. Okay, so that's what that function space means. So up here, we only use p equals 2, and we use p equals 2 here, but notice that for the function itself and for its derivative, we use different Hilbert spaces here and here. Here we use the original Hilbert space, and here we're going to use this dual. Okay, so yeah, we can do that if we want. Suppose that U is a weak solution to the diffusion problem, then U actually is a continuous function, not just a strongly measurable function now. This is kind of like a Sobolev type embedding. So I will put here Sobolev-like. So I have a function that is in this space and this space. It turns out if you have a function that has the property that it's in L2, 0t, H01, and its derivative, weak derivative exists and is in this space, then the function itself has to be in this space. That's a Sobolev-like embedding. It's a continuous function from 0 to t into L2. What that means is I can think about U as a map from 0t into L2, and this mapping is continuous. Well, what do I mean by continuous? This is the usual topological or point set version of continuity. So you can whip that out. It works just fine in the setting. So that's what we mean by saying this. It means that this map has to be a continuous mapping. Okay, it's not just measurable anymore. It's something a lot better. It goes from 0 to t, not in any of the two spaces that we had above. The two spaces that we have here and here are in one case, this is like the space of all weakly differentiable functions, or I should say, this is the space of all functions which are one times weakly differentiable. This is the space of functions which are like minus one times weakly differentiable based on the hierarchy I showed you above. So L2 sits right in the middle of these two. L2 is like smack dab in the middle, and so that's why it appears there. So I'm not going to go through that proof. That proof is in that book by Evan that I referenced earlier, Partial Differential Equations, and it has all the details. We're going to skip them here. What's important for me is that if we have a weak solution to the diffusion problem, then I can show this type of estimate. And this type of estimate is what we call an energy estimate. And the best way to explain what's happening here is just simply prove the estimate and not worry about the weird statement of it up here. If we prove it, you'll see it. You don't have to think about it. Okay, so these are what we call energy estimates, here and here. Notice that the right-hand side is exactly the same in both locations. This guy is bigger than that. It's also bigger than that. And so I'll show you why. Show you why that works. If U has additional regularities, so this is additional regularities beyond those assumed for the weak problem. So in other words, if the spatial part of U is better than H01, but then actually H2, and the temporal derivative, the spatial function is there, its derivative is in not H minus 1, but actually L2, and assuming that the initial data are better than L2, assuming that the initial data is weakly differentiable, and in H01, in fact, then it turns out U is a continuous map from 0t into H01. And we have these energy estimates. So this is all fancy schmancy business for saying things which turn out to be rather easy. And so this looks complicated and hard. It's actually very easy. And I'm going to show you why. Now, remember I said here, this is proved in Evan's book. We're going to skip the proof of that. So that's what I mean by the reference there. You can find out why this is a continuous map in Evans. Now, let's just use that and start with this, and let's see what happens. So if we start with the weak formulation, and we put in as a test function phi equals u, the question is that allowed? Well, phi is a spatial only function. Can we put in this time-space function? The answer is yes, we can do this because in the spatial sense, this is an H01 function. Okay, U is an H01. We have to go back up to recall that it's H01 in its spatial component or its spatial extent, and therefore we can substitute it in for the test function. Now, also from Evans, we're going to look at this term first. In Evans, it says that if you have this term here and you know that U is in L20TH 0, 1, and the derivative exists and is in the space L2 0t h minus 1, then this is actually differentiable. It's at least weakly differentiable. Well, actually, no, that it's differentiable in the usual sense. Okay. And so I can take the derivative of this term here, and I can show that it's actually equal to that. Okay, so this is just a number, and I can show this. I hope so. Let me see if I can show you a little non-convincing proof of this. So let's just look at that. What is that? That is just we can drop the hat. Well, let's put the hat. So I'll show you a quick little proof. There we go. What does this mean? This means 1/2 d by dt. So it's the u norm squared, but what? Oh, that's not right. It's not the temporal norm. It's space only still. It's the spatial norm. And I'm going to write this as, instead of writing u squared, I'm going to write it like that. So that's what that is, right? Now pass the derivative through, and we're just going to assume that everything is differentiable in sight. What do we get? We're going to get a partial derivative on u times u. These are spatial derivatives. And this is another partial derivative. If these were if these were classically differentiable functions, they're the same thing. And I can combine them together to just give the result that I'm looking for. Which I could write as in the L2. So that almost looks like that, right? How close are they? Well, they differ because this guy is not a classically different. This guy's not a function in the usual sense. It's a functional. But I can still prove this sort of form. And this is why this duality pairing notation is so useful, because it looks like the L2 inner product. It's still true. Okay, so this is still true. Even though our proof down here won't work to show this, this fact is still true. So we're just going to take this as being the truth, even though this proof here doesn't work. Fine, well, let's just put this away for now. Our proof doesn't work, but the idea is the same. All right, so this term just turns into that. So let's replace it. There we go. Now this term, what is that? That is the H01 norm squared. And this is still the inner product of F with U. Now again, this one is, it's the spatial inner product. We're not talking about any temporal inner products or anything more fancy than that. Okay, now here's where the estimate really builds. So now if you believe this, which comes from Evans, this is simple, this is simple. Let's apply to this side, let's apply Cauchy-Schwarz. So this is less than the L2 norm of F times the L2 norm of U. No problem there. Let's raise this L2 norm from an L2 norm to an H01 norm. How do we do that? Well, we can use Poincare inequality to do that. In fact, this would be the Poincare constant in this case. I have a typo here. Let's fix that quickly. That 2 should not be there. Not yet, at least. Now I'm going to pry these two things apart. And the idea here is I'm going to get a term over here that involves u, but I want to put everything that involves u over on this side, the left-hand side. So how do I do that? I'm going to use the algebraic geometric mean inequality to do this. So here's the usual algebraic geometric mean inequality. AB is less than 1/2 a squared plus 1/2 b squared. I showed you how to prove this previously. We're going to use a variant of that, which says that AB is less than epsilon over 2 a squared plus 1 over 2 epsilon b squared for every epsilon greater than 0. If you've never seen the proof of this guy, it follows directly from the proof of this, just with a little trick. Some people call it the rob Peter to pay Paul trick, but in any case, it works. I can just take this and out comes this guy if you know that clever little trick. So we're going to apply this guy with epsilon equals to c, the same c that appears out in front, the Poincare constant. Fine. It holds for every epsilon, so it's definitely going to hold for my Poincare constant. So I'm breaking this and this apart, keeping this intact. What happens? Well, this c is going to hit on this 1 over c and just produce the 1/2. Okay, 1/2 u h01 norm squared. And notice over on this side, I have an h01 norm squared, but without the 1/2. So what I'm going to do is I'm going to subtract the 1/2 u norm from both sides. The inequality is still the same because I'm just subtracting. I move this guy over to the other side. That gives me a 1/2 there. That goes away. No problem. The directions of inequality are still the same. And this is the only thing that remains on the right-hand side. Now, everything in the inequality has halves. So multiply by 2. And if I multiply by 2, I go from the thing that we were just dealing with to this inequality. Okay? So once I get beyond those two first quirky things involving these weird formula, and this guy here, then everything is kind of basic. Now, you do have to be a little bit more careful. We're not taking 100% care, not all the care that we should take, I suppose. And we're proving this like applied mathematicians, not like PDE analysts would, who would be very, very careful on doing this. But in any case, all these things can be justified, all these steps. Next step is we're going to integrate this inequality from t, in t from 0 to some number, some time instant s in the interval 0 to t. Right? I'm just going to do everywhere 0 to s, integral 0 to s, integral 0 to s. Well, how do I know these inequalities still hold? Because these are positive quantities. And if I have one positive function greater than another positive function, I integrate them up to s, then the integrals inherit the same inequality. Now, it just so happens that when I integrate a derivative in time, what do I get? Well, that's the fundamental theorem of calculus. When I integrate a time derivative, I just get the evaluation of this function at the endpoints. What are the endpoints in this case? S and 0. And so the result of doing that integration on this term gives me us L2 norm squared minus u0 because I'm integrating from 0 to s L2 norm squared. This term I can't do anything with. I'm just going to leave it in its form. Integral 0 to s, that norm, same as there, dt, is less than, I can't do anything with this guy either. I'm just going to leave it in its form. Okay, so this here, just keep in mind, this is a spatial norm, And the whole thing gives me those weird norms that I was defining or describing above. So now this term here, what is that? U0. Well, that's just V. So V is what we call data of the problem. It's a known quantity, so I'm going to take this as V and I'm going to move it to this side. And so this is the inequality that I now get. And it starts looking almost like what we want. Let's think about how do we prove the max, this guy here is less than this stuff. Well, I could drop this if I want, because if that's a positive quantity, so I know that this is definitely still going to be less than that, even if I drop that. Because if I drop this guy, then this is smaller than the sum of those two things. So this guy is less than this and that. Let's integrate this guy all the way up to t. That gives us something which is bigger. That gives us something that's bigger. What that says, if I drop this and consider only what's over here, then I see that what I get is u of s L2 is less than the L2 norm of v squared plus, remember I said I'm going to push that guy all the way up to t. Now, might look like I've just done a trick here. All I've done is push this guy up to t and drop that term. But I have this. But this says this is true for every s, regardless of what s is. For all s in 0 to t. Didn't matter what it was. That holds. Well, now I can take the maximum of this. Its maximum exists, and I can take it because how do I know it exists? Because this u was a continuous map from 0t into the L2 functions. So its maximum exists, and I can take that maximum. I know that this is true for every s, so I know it's true for the maximum. Therefore, I get this is less than that. That's the maximum. Now, what about the combination of this term? I could drop this one separately and show that, well, okay, now I know that this, if I run both of these sides up to t, that's just going to be this is less than that. But now, why is it possible, or how do I know that the sum of these two things is are less than the sum of the two things on the right? How do I know that the sum of those two things are less than the sum of those two things on the right? So I'm going to leave this as a little exercise for you guys to show. I'm simply going to say that this implies that this is true. So this is what we call an energy estimate or energy stability. Energy estimate. Um, why do we call it energy estimates? Because I can think about it like this. I can think about this as being the energy of the system. And we're going to talk more about this next time. So don't worry about it if you don't understand what exactly I mean there. So we can kind of think about the energy of the system as being like that. This is the amount that the energy is dissipated. And this is the amount of energy that's added to the system. This is like the change. I guess I said that kind of wrong, right? Well, yeah, I'm saying this a little bit wrong. So what I want to do is I'll come back to and I'll explain why this is an energy estimate next time. So um, forget about my poor little description there. It'll make more sense next time, and I'll uh, bring in a more concrete description. For now, just accept that it's an energy estimate. Okay, I have to do a little more to make that clear, I think, next time. Okay, so but if it's okay setting that aside for now, we can finish the rest of this estimate. And the rest of the estimate says that if I assume that I have better regularities, then I can then show that U is actually a continuous map from 0t into this function space. Again, we're not going to prove that. We're simply going to refer to Evans on that. but that at least allows us to write the weak form in a slightly better way. We can replace this, what was the dual pairing before, with a simple inner product. Okay, because it's in better regularity, this thing is actually going to be now an L2 function. So it makes sense to combine an L2 function and an H01 function as we did uh, many times before. This is the standard test function, phi. And so now we know that the spatially U is in H2. Um, I should say this is spatially true. So this is not really I should fix this guy up here. This is a little confusing. U is not really in this space. It's for every T it's in that space. Okay. Well, let's see. Is that kind of like that? So I need to think about a better way of saying this. This is not exactly correct, but I'll fix the notes and I'll not exactly right. But I could kind of think about it in that sense. Um, so in any case, I can I can think about this object called the Laplacian of U, and that's actually an L2 function in space. Um, the good news is that can be used as a test function. So the test function can be anything from this space, and this will work for that. So I can put that in as a test function in the place of phi. Right. Okay, so do that. And then we're going to do our usual integration by parts. We're going to first, I'm going to take one of the derivatives that was sitting here, and I'm going to throw it in front of that u there. And don't worry about the math now. Just assume that it can be done in the usual integration by parts way. This one I don't have to integrate by parts. That's already in a nice form that I want to use. But okay, all I'm going to do with integration by parts is move that guy over. Now, you might get worried, oh, that derivative is going to move in front of there. It is, but then I can interchange the two derivatives. And when I do that, I get this. This is just the Laplacian of u L2 norm squared, and this is the same as it was. I can show, like I did above, that this is just equal to 1/2 the time derivative of grad u grad u. Okay, or in other words, the time derivative of the L2 norm of grad u squared. This is L2 norm of Laplacian u squared, and that is what it was. Now we're going to do our old analysis stuff. So I'm going to do Cauchy-Schwarz, break that up into an L2 and L2 of Laplacian of u. I'm going to use the algebraic geometric mean inequality. This time I don't have to do anything, no special algebraic geometric mean inequality. I'm just going to use 1/2, 1/2. So this breaks up as 1/2 L2 norm of f squared, 1/2. And again, this is just the spatial L2 norm, 1/2 Laplacian u spatial L2 norm squared. I can take this guy, and the trick here is what we call hiding. We're going to push that term back over to the other side because that is, I want everything in U on one side and all the data stuff on the other side. So if I take that over to the other side, okay, I get a half now on Laplacian U, but I have then a half left over for every other term. I'm going to multiply by 2. That gets rid of it. And so I end up with this. And then playing the same game that we did last time, you integrate over time, and you make your arguments and show that you have the estimates that we claimed, namely that estimate and that. So I'm going to leave that to you to show that. We'll skip that part. All right, so that'll be a homework exercise. Finally, well, actually, before I do that, let's take a pause here. And you can turn your cameras back on and let's see if you guys have any questions about this.